This Module 5 video continues the discussion of catalytic cycles in organometallic chemistry in the context of catalytic hydrogenation of alkene with rhodium catalysis. The previous video described how this rhodium complex was formed in 3 steps. This complex has 6 ligands attached to rhodium. It is hexacoordinate. The chloride and 2 triphenylphosphines come from earlier in the catalytic cycle. The 2 hydrogens come from oxidative addition of hydrogen gas. And then the alkene is coordinated to rhodium. Notice that the bulky triphenylphosphine groups are on opposite sides of the rhodium coordination sphere. These are trans. That is the sterically most favored geometry. In the migratory insertion reaction, one of the ligands that is negatively charged attached to rhodium migrates to the alkene. Rhodium then forms a sigma bond at the other carbon of the alkene. This does not change the formal oxidation state of the metal, but it does reduce the number of ligands by 1, because the hydrogen atom and the alkene ligand have now combined to form a new single alkyl ligand. At the bottom of page 4 of the worksheet, the question is asked, what is the total valence electron count for this product? We'll discuss that in class, along with discussing how does this transformation resemble the hydroboration of alkenes. Turning to the last page of the worksheet, the final step of the catalytic cycle is reductive elimination. In the reductive elimination step, 2 of the ligands attached to the transition metal form a 2-electron single bond, with 2 electrons returning to an empty orbital on rhodium. This regenerates chlororhodium bis-triphenylphosphine and releases an alkane product, in which the elements of dihydrogen have added to the pi bond of the alkene. In class, we'll review the formal oxidation state of rhodium and the total valence electron count. The worksheet concludes with a question. Reductive elimination has a significant geometric constraint, and we'll discuss what that is in the class meeting. I'll conclude this video by showing the catalytic cycle once more. Wilkinson catalyst is actually not within the catalytic cycle, which is steps 2, 3, 4, and 5. Rather, Wilkinson catalyst is actually a pre-catalyst. This enters the catalytic cycle by dissociation of a sterically hindered triphenylphosphine ligand to give chlororhodium bis-triphenylphosphine. All of these steps are in equilibrium. In most cases, 1 atmosphere of hydrogen pressure does oxidative addition with rhodium prior to alkene coordination in step 3. But if the hydrogen pressure is low, the alkene will then coordinate with rhodium, with oxidative addition of hydrogen occurring after alkene coordination. Also, all of these steps are reversible. With some heterogeneous palladium catalysts, the same type of mechanism occurs with oxidative addition of hydrogen, coordination of alkene, migratory insertion, and reductive elimination. But with the heterogeneous palladium catalyst, which is more stable at high temperature, we can actually run this catalytic cycle in reverse by adding the alkene to the palladium catalyst, undergoing oxidative addition to a carbon-hydrogen bond, beta hydride elimination, which is the microscopic reverse of migratory insertion, alkene dissociation, and reductive elimination to generate hydrogen gas. In fact, this is how most commercial hydrogen is generated, coming from alkanes from fossil fuels, but in addition to generating hydrogen, also generating terminal alkenes, which are useful starting materials for some of the chemistry discussed in this class and for polymerization reactions that you will study in Chemistry 204. This concludes the videos for Module 5B on catalytic cycles and catalytic hydrogenation.